right, so we have been learning all about how to describe charge distribution, and we've been talking about it in two totally different ways. Charge distribution as relates to an electric field, charge distribution as it relates to an electric potential. And we used electric fields to describe potentials, and we talked about potential energy and all these things in the lecture on electric potential. Now we're going to kind of like narrow everything in and just make sure that we're very succinct in thinking about how is an electric field related to an electric potential. How can we use the idea of fields to get potentials? And we're going to explore a couple of cases, one of a uniform electric field and then one of a point charge. So how we can describe charge distributions in a space with electric potential and electric fields. They then must be related to each other. Potential and fields have to be related. So let's look at that relationship. And we're going to do that first, like I said, in a uniform electric field. So we're going to use the case of a uniform electric field. Now, when we talk about electric potential energy, we knew we could describe a particle's electric potential energy in terms of its positional change within an electric field. So we're interested in potential energy. It's always about the change in potential energy that we really care about when we're dealing with energy. So we want to remind ourselves that that change in potential energy, and this is our electrical potential energy, I will drop that U in a little bit since we're in this space, but is from our previous discussion, we learned that that was equal to the charge times the electric field that charge is in times the position of that charge. All right. We also learned that our electric potential was a way to describe the electric potential energy in a normalized way. So we know that the electric potential, remember, was the electric potential energy per charge, okay? So that's the way we describe the electric potential. If we combine these two ideas, we then also know that our change in potential, our potential difference, which we also call voltage, is equal to that change in electric energy per charge. And I'm going to rearrange this equation. This tells us that our change in potential energy is our charge times our change in electric potential, or our voltage. Remember, our change in potential, which we kind of been using kind of a bold V. This is that voltage. All right. Okay, so now I'm going to kind of combine these two relationships, and we find that our voltage is going to be related to an electric field. So I'm going to look at these two relationships combined. We have minus Q. Let's do the bottom one first, so it's in the right order. So Q times my voltage, potential difference, is equal to, so that's this delta U, is equal to minus Q times the electric field times D. And when I do that, I find that my potential difference, or my voltage, is equal to minus the electric field times D. So this is a way that I can describe electrical potential difference, voltage, in terms of my electric field. So let's just do a quick little example. A couple of things. This minus sign does give us some information that I want to alert you to. This tells us that the electric field is pointing in the direction of decreasing potential. Lost my train of thought for a second. So, high to low. Okay, so this actually gives us a little bit more information that we haven't talked about yet, which is that when I have a potential difference, this negative sign gives rise to the fact that that potential, that electric field is going to point from an area of high potential to an area of low potential. So that's a new little bit of information that we want to kind of squirrel away and discuss. So let's do a quick little example. It'll be very fast, just to familiarize yourself with this relationship. I'm just gonna pop that example up here. So let's imagine we have two parallel plates and they're charged to produce a potential difference of 50 volts between them. So what does that look like? So here I have one plate, another plate. We'll say this one is at a higher potential than this one. So I'll label one a positive potential, one a lower potential. And the potential difference between these two, or the voltage designated by these two plates, is 50 volts. All right. If we are going to draw the electric field inside those plates, we would draw it in the direction of high to low. We learned that in this situation here. Now, if I have infinitely long plates and they're really close together, this actually does give us a uniform electric field in the space that we're going to really be caring about. Okay, a lot of information there. That's our piece of information. These plates are separated, so the distance between these two potentials is 0.05 meters. What's the magnitude of the electric field between them? So we're just going to use our relationship here. We have our voltage of 50 volts, our potential difference. Our D is 0.05. So we know that delta V, or our big V, is equal to minus the electric field times D. If I solve for the electric field, I get V divided by D is equal to the electric field. So I have 50 volts over my distance of 0.05. It is negative, which again is our direction. This is what that tells us. And that equals the electric field of 1,000 volts per meter in magnitude. So this just tells us this information. All right. So the electric field strength is 1,000 volts per meter. It goes from high to low. So this is our answer for the magnitude of the electric field, which is what it's asking for. All right, 1,000 volts per meter. Now that's a new unit. Does that unit actually make sense? I'm going to go real quickly over that, why that unit makes sense. I'll do that here in the middle, and then we'll look at what happens if I don't have a uniform electric field. All right. So, does this unit of volts per meter make sense for my electric field? Now, when we first learned about electric field, we learned about them in the case of static charges. And we learned that the electric field was the newtons per coulomb is our usual unit of electric field. Looking at the forces, remember the electric field is the force times the charge. And forces in newtons, charges in coulombs. So we're used to seeing the electric field, and I'm going to use these three to designate this as a unit, of newtons per coulomb. All right, so the question is, does it make sense to have an electric field of volts per meter? Okay, well, we're going to do a reminder of your Physics 1 stuff where we did dimensional analysis. Newtons per coulomb, if I just multiply meter over meter, so pop that in there, doesn't change anything because these two meters kind of cancel out, right? And I'm still left with newtons per coulomb. But what does it help me? Well, it gives me a Newton meter. And a Newton meter is work, which is in joules, right? So this gives rise to Newton meter is also a joule. So this is a joule per coulomb times meter. Well, a joule per coulomb is energy per charge. Energy per charge. That's a volt. And sure enough, since joules per coulomb is a volt, volts per meter works. So just to remind you of that dimensional analysis skill that you've learned in Physics 1, and to make sure that we're always kind of being attentive to those units and does it make sense. One more reason, fields and potential are related, kind of another way to be looking at that. Okay, nice. So what happens if I don't have a uniform electric field? What about a point charge? Can we get the electric potential of a point charge? Well, we can, because we know that point charges produce electric fields, and if there's an electric field, there's got to be an electric potential again, because we describe charge distribution in that way. So let's look at that situation. Because what do we also know about the electric field produced by a point charge? And if you need that friendly little reminder, go back to that first time we introduced the idea of an electric field. We know that a point charge, the electric field changes the further away you get from the point charge. So it isn't uniformly distributed. In contrast, it's kind of changing with distance from the point charge. So how do we manage that? How do I get to look at an electric potential when my electric field is non-uniform? And we're going to use, like I said, a point charge as that example. So non-uniform electric field, and we're going to use a point charge. All right. Oops. And I'll go ahead and get rid of this problem for us. And we'll just go back up to thinking of what we're thinking about. Okay. So let's recall kind of foundationally, we started again with that potential energy idea. Remember, a potential energy is, well, the change in potential energy for a non-uniform area really is this idea of an integral, right? We're looking at how potential changes along a path of the force along that path. And we take a little bit of pieces of that path. So that's, again, back in our kind of Physics 1 world. So if we are going to look at a reminder, again, same thing we had before. We have our potential is equal to our potential energy per charge. And we also know that for electrical forces, that the force relationship in terms of the field, we know that the electric field is equal to the force per charge. Okay, so we go back to our electric forces in relationship to fields, and our force was equal to the field times the charge. So that means our field is equal to the force times the charge, divided by the charge, and we know that our electric potential is our potential energy per charge. So field is force per charge, potential is energy per charge. Okay, so that's kind of another way to kind of think of them two related. If we put these ideas all together, we get, and I'll walk through this sort of stepwise with you. We'll start with this relationship, our line integral, the force dot dl. That's going to give us, if I use this, we have Q times E dot dl. So I just plugged in my force per charge into my force relationship. Q is a constant, of course. I can pull that out of my integral. And I end up with my electric potential energy, change in electric potential energy, related to my electric field, okay? For a non-uniform electric field, I look at, the integration across the small distances. We'll use L in this case. All right, so I have that. We also know that my change in potential, voltage, is equal to my change in potential energy per charge, which, like I did previously, is my charge times my change in potential, voltage, gives me my change in potential energy. So I'm going to plug this in here. We end up with Q delta V. It's my change in potential, is equal to Q times the integral of the field. So this is not a whole lot different than our uniform electric field, but I'm doing it in a more generic way with the electric field being non-uniform, and we're having to look at the change through the integration across small lengths, small distances. Q's, of course, cancel out here, and we get our change in potential, voltage, equal to the integral of the electric field dot dl. Okay, that's powerful. That's powerful because now what can we do with this? This is telling us, again, the potential difference or the voltage in general, its relationship to the electric field for a non-uniform electric field. With a uniform electric field, E just pops up, the integration across dl is d, and we get the relationship we already got because the electric field is constant, so it comes out of the integral. So we could have started this way with a uniform field, but I wanted to just not have to think about that calculus yet. All right, so let's look at a point charge. Okay, so point charge. We know that I'm going to change colors. We know that the electric field for a point charge is equal to KQ over R squared, right? The electric field for a point charge is KQ over R squared. We learned that in our static our static electricity information. So now we're going to take this information, we're going to put it into our integral. So our potential difference, voltage, is equal to the integral along the radius now, so from A to B, where R is now our unit of measure, of KQ over R squared dr, R being that unit of measure now. We know K and Q are constant, so we really have to take those out of the integral. Sorry, I think I dropped my negative sign. Right here, way back here, we dropped that negative sign. That, my friends, is not good. But that's okay. It's okay. We just kind of got a little quick. Got to keep those negatives in there. And it's all good. It's all good. It's all good. All right. Ugh, didn't want to lose that negative. Okay, which means we need to make sure it's in here too. All right. Our potential is, I got ahead of myself, or behind myself when I realized that negative is lost. Really just left it off. So we want to make sure we pay attention to that negative. We take KQ out, and now, we can put the minus in front of it. The integral from A to B, of course, of 1 over R squared dr. All right. Now, one more piece of little information that we got to add into here, because we talk about, whenever we're talking about change in potential energy, like our gravitational potential energy, we always set a reference 0 point. For gravitational potential energy, way back when you did that in physics 1, we often said the ground. The ground's going to be our 0 point, or the lowest point of the hanging pendulum, that's going to be our 0 point. We get to set that 0 point. So we're going to set that 0 point here for potential as well. When we think about the influence of a field, let's say for a point charge really, really, really far away, it's pretty small, right? If I put a charge really, really far away from another charged particle, very little influence. We could talk about that as the potential for those two to interact or to change each other's energy is really, really small. And so by convention, we tend to say that at R equal to infinity, that is our set point of 0 potential. Okay, so our potential at infinity is 0. All right, so as we look at this relationship for a point charge, we're gonna go from some value all the way out to infinity. So we're gonna get to B being way, way out to infinity. And so as I continue with this integration, we find that the solution of this integration, of course, is 1 over RB squared minus 1 over RA squared. Okay? And when we do that, get rid of those bars. All All right, so that's the solution of the integration. Our infinity, this number, of course, 1 over infinity is 0. Okay? So our v of b minus v of a, we also know that this indeed is 0, right? So we end up with only worrying about the single potential, the voltage, is equal to kq, not the voltage, the potential, sorry, the potential difference, we're still in the difference, potential difference, kq over r, where RA is the distance that we're starting from going out to infinity. So because the radius is infinity, this goes to 0. We also talk about potential B being at 0, so 0 minus whatever gives us just the potential at A is equal to KQ over R. All right, a little cumbersome there at the end, sorry about that. So I will just recap very quickly, then we'll do a quick problem in this space as well. So the idea of a non-uniform electric field, we're going to use this generic relationship of looking at the change in potential, the potential difference, the voltage, as a function of the integral of the electric field along the line that we are looking along. And so as our example is a point charge, we know that the electric field of a point charge is kq over r squared. We can use that integration. We also recognize that the potential difference, or the potential really, really far away is 0. That also plays out in our math and in our integration of 1 over r squared. And we get this idea that potential, the voltage of a point charge, is kq over r. So now we can use that, and we will use that in an example. We can do this for any charge distribution, a ring, a cylinder, whatever that charge distribution is, we can do that integration to find it. And so that's something to kind of keep in mind. We're not going to do that necessarily in this class, but as you move on in electrodynamics, that integration is certainly going to come back. All right, let's do a quick example with a point charge, and then we will be all set. Get this erased. Clearly, it was time to use a clean eraser. All right, so I'm going to look at another problem, just an example of a point charge and determining the electric field, the electric potential, using the relationship between electric field, electric potential for a point charge. So let's pop that question up. So what minimum work must be done by an external force to bring a charge of 3 microcoulombs, so 3 times 10 to the minus 6 coulombs, from really, really far away into a point that's only half a meter from a charge that's stationary? So you can imagine, here's our situation. We have a stationary charge here. That stationary charge, Q, is 20.0 microcoulombs, which is 20.0 times 10 to the minus 6 coulombs. And I want to bring another charge, a really tiny charge, 3 microcoulombs, in from infinity to within 5 meters of this charge. So I want to bring my small q, which is 3 microcoulombs, or 3 times 10 to the minus 6 coulombs. And I want to bring it within a half a meter. All right, perfect. So how much work is that going to take? Okay, so how do we tackle this problem? We want to remember what work means back from our previous little conversation in electrodynamics or our old material in, Physics 1. It tells us that the work is equal to our change in potential energy. And we know our change in potential energy is equal to Q times our change in potential. All right? So that tells us that our work, the work we need, is Q times the potential at the final minus the potential initial. Our initial is when it's way, way out here. We know the potential at infinity is our reference point. So that equals 0. So we're left with the work equaling Q times our potential final. Okay, we don't know our potential final. But what do we know? We know that the potential from a point charge is given by K, Q over R. So we end up with little q times K, big Q, all over the radius between them. So the potential from this point charge on this Q, this little q here, is given by K, Q over R, and that is the charge that we're doing the work on. And so we have Q of 3 times 10 to the minus 6 times K, which is 8.99 times 10 to the 9th times our charge all over the radius. Oops, not 0.5. So we have 1.08 joules of work is needed to move that point charge Q in to being this close to our stationary charge. That's the change in energy that we put on charge little q, and therefore the work. And it's got to be related to the potential in that area. All right, so using those relationships. Lots in this mini video lecture and examples. Good job.